The room is dark, the monitor glows blue, and far from home a gold mirror hangs in the cold. The subject is James Webb, a telescope so sensitive it cannot simply turn around and stare at Earth. What it has learned from worlds our size is forcing scientists to rethink how our own planet would look from far away. And that is where this story opens. Stay close to this channel for space stories that turn huge discoveries into clear ideas you can carry with you. At first, the title sounds almost impossible. Webb sits about 1.5 million kilometers from Earth, out near the Sun-Earth L2 point, and it survives by keeping a 5-layer sunshield between itself and the heat of the Sun, Earth, and Moon. NASA describes that shield like sun protection at the level of SPF 1 million. So no, this telescope was not built to swivel around like a tourist and snap a family photo of home. And yet, in a deeper way, James Webb has been looking back at Earth from the moment it started studying rocky planets. Not by taking a direct picture of our oceans, our clouds, or our city lights, by asking a harder question. If Earth were only a tiny signal near a bright star, what would a telescope like this actually notice, and what would it miss? That question matters more than it sounds. For years, many people imagined that once Webb came online, the road to another Earth would be straight. Find a small rocky world, read its air, spot a few gases, move one step closer to life. To see why this matters, we need to step back. Most people believe the hardest part is finding a small planet at all, and that once a telescope as powerful as Webb locks on, the atmosphere of an Earth-sized world should begin to give itself away. A nearby red star, a rocky planet, a careful measurement, and the path seems almost laid out. That is the picture we need to hold for a little while. Webb did not arrive as just another telescope. It arrived as a kind of promise. A machine built to work in infrared light, which is the heat glow many worlds give off even when they are too dim to photograph, the way a phone photographs a face. That made people wonder if the age of guessing about small planets was finally ending. Earlier observatories had already changed the game. Hubble and Spitzer had shown that you do not always need a clean picture of a planet to learn something real about it. Sometimes you watch a planet cross in front of its star. Sometimes you watch it slip behind. Then you measure the tiny change in light and pull the planet out of the glare like a whisper out of noise. Webb was made to do that with more precision and across a wider spread of wavelengths. NASA says it can cover ranges from 0.6 microns to 2.8 microns in a single shot with some instruments, and it also reaches farther into the infrared with others. To a scientist, that means fingerprints. To the rest of us, it means the chance to tell whether a distant world carries gases, heat, clouds, or almost nothing at all. Before the rocky planets became the headline, Webb proved it could read a giant world with shocking detail. In 2022, observations of the hot gas giant WASP 39b showed water, carbon dioxide, and even sulfur dioxide. NASA called it an exoplanet atmosphere as never seen before. It was a loud success, the kind that made the future seem to rush toward us. That mattered because it told researchers the machine was alive in the best sense. Its eyes were sharp. Its instruments agreed with one another. Its methods worked. If Webb could do that to a giant bloated world, many people assumed the only thing left was patience before it did something just as dramatic for a rocky one. And the rocky worlds everyone kept circling back to were around small stars called M dwarfs. These stars are cooler and dimmer than our sun. That sounds helpful. A dimmer star should make a small planet easier to notice, the same way a candle stands out more in a dark room than in noon sunlight. That is why systems like TRAPPIST-1 became so important. You did not need to explain the whole map to feel the pull of it. A small star, several rocky planets, some in the habitable zone, which means a place where temperatures could allow liquid water under the right conditions. It looked like the neatest doorway we had into the dream of another Earth. Scientists talked about atmospheres because atmospheres are where possibility begins to sharpen. Air changes temperature. Air carries clouds. Air traps heat, or fails to. Air can hold chemical hints that tell a story about rocks, radiation, weather, and maybe, with great care, biology. Nicole Lewis explained the promise and the limit in clear language back in a Quanta interview. Webb, she said, would not give us pretty pictures of these planets. It would not show continents or shorelines. What it could do was search for signatures in starlight passing through a planet's atmosphere, the way smoke tells you there is a fire, even if you cannot see the flames. Marcia Ricci, one of the scientists tied closely to Webb, framed it another way. Webb was a major step, but not the last step. Future telescopes, she said, would be the ones aimed at proving we had found a truly Earth-like planet capable of hosting life. That warning sat there quietly, even during the excitement, but most people heard the excitement louder. And excitement was easy to understand. Webb was far from Earth, cold, shielded, and stable. It was built to avoid the heat coming from the Sun, Earth, and Moon, because heat is noise to an infrared telescope. That same design that keeps it safe also limits what it can point at. In other words, the machine most people wanted to look back at Earth is the very machine engineered not to do that. That sounds like a frustrating limitation, but it is really a clue. If Webb cannot directly study Earth as a bright nearby target, then scientists need a stand-in. They need distant rocky planets that are close enough to measure, simple enough to read, and quiet enough to trust. Those worlds become a mirror held up to home. This is where the assumption grows stronger. A small, rocky world around a dim star should be the easy version of Earth hunting. You do not start with a pale blue dot around a sun-like star. You start with the more generous setup. A red dwarf, a tight orbit, a bigger signal, and a planet that should, in theory, tell you what kind of air it wears. By the time Webb's early exoplanet work settled into public view, the path seemed obvious. Study the giant planets first. Use them to test the instruments. Then move down toward the smaller, cooler, more interesting targets. Like walking from the loudest drums in an orchestra to the faintest flute, but trusting that the room is quiet enough to hear both. Even the methods made it feel reasonable. If a planet moves behind its star, you can subtract the star's light from the combined light and estimate the planet's own thermal emission, which means its heat glow. That sounds almost magical, but it also sounds clean, like the kind of trick that should keep working as long as you are patient enough. There was also a human reason this story felt ready. We wanted it to be ready. The idea that the universe would finally hand us a nearby rocky world with readable air fit the mood of the time. A better telescope, a better signal, a better chance to ask the old question in a new voice. So the assumption sat there, solid and comforting. Webb had the sensitivity. Nearby small stars had the right geometry. Rocky planets would be difficult, yes, but not unreachable. And if any path led back to a clearer picture of Earth from afar, this looked like the one. Then the first close looks at rocky worlds began to bend that picture. The problem was not that Webb was weak. The problem was that the universe was more slippery than the clean diagram. The easy road to another Earth was about to stop looking easy. Write the moment your old picture cracked in the comments. That one line helped shape the next story around the exact part where curiosity turns into real understanding. What we had just taken for granted turned out to be a small part of a much larger story. The next observations would show not that Webb had failed, but that the very worlds we hoped would teach us about Earth were hiding their truth in a much thinner, harsher, stranger way than expected. The reveal did not begin with defeat. It began with proof of power. Webb's work on worlds like WASP 39b showed that when a planet has a big inflated atmosphere, the telescope can read it with astonishing clarity. Expected signal, strong result, loud chemical fingerprints. It was like hearing a singer clearly in an empty hall. That early success mattered because it made the next silence harder to explain. If the telescope could pull sulfur dioxide, water, and carbon dioxide out of a giant world's air, why would a rocky world remain so stubborn? The obvious answer was size. The deeper answer, which took longer to settle in, had to do with the kind of atmospheres Webb is best at seeing. Then came one of the most startling milestones in Webb's exoplanet work. NASA said Webb had made the first thermal emission observation of any planet as small as Earth and as cool as the rocky planets in our own solar system. The target was TRAPPIST-1b. Just that sentence alone sounded like science fiction had leaked into the lab notebook. Thomas Green of NASA Ames, Taylor Bell of Berry, Elsa Ducrot of CEA, and Pierre-Olivier Lagage of CEA were among the researchers tied to that work. The paper appeared in Nature in 2023. What astronomers expected was not certainty, but room. Maybe a thick atmosphere, maybe heat being moved around the planet, maybe some sign that air was softening the extremes. What Webb actually found was harsher. The dayside brightness corresponded to about 500 kelvins, roughly 450 degrees Fahrenheit. That temperature fit a picture of bare rock with little or no significant atmosphere to spread heat around. Instead of a wrapped world, it looked exposed. Like lifting the lid on a pot you expected to be steaming and finding the water gone. That mattered for reasons bigger than one planet. TRAPPIST-1b is not Earth. It orbits much closer to its star and gets far more radiation. But it was one of the first times Webb had reached down to the scale people care about most, a small, rocky world. And the first strong answer was not, here is an atmosphere. It was closer to, here is a surface taking the full hit. Scientists kept going, because one world never gets the final word. Soon attention shifted to TRAPPIST-1c. Again, the expectation had room in it. Maybe this one carried a thick carbon dioxide atmosphere, something more like a heavy blanket than empty stone. Maybe this was where the measurements would begin to look less brutal. Instead, another surprise arrived. NASA reported that Webb ruled out a thick carbon dioxide atmosphere for TRAPPIST-1c. Its dayside temperature came in around 380 kelvins, about 225 degrees Fahrenheit. That made it the coolest rocky exoplanet ever characterized by thermal emission at the time. Expected greenhouse wrap, actual lean signal, result closer to a stripped world than a Venus-like one. Sebastian Ziba led the Nature paper on that result in 2023. The numbers did not say there was absolutely no atmosphere of any kind. They did say there was no thick carbon dioxide cloak doing the obvious work many people had imagined. Think of checking a house in winter. You expected thick insulation in the walls. What you found was a room losing heat almost directly to the night. Now the story had shape. Webb could reach Earth-sized territory. It could measure heat from rocky planets. It could tell us something real and new. But the real and new thing it was telling us was not that small nearby worlds were opening up neatly. It was that some of them were dry, hot, bare, or at least far less protected than the hopeful sketches suggested. That raised a harder question. Was Webb finding a truth about these particular planets, or was it running into the edge of its own strength? The answer, frustratingly, was both. And that is where the title of this video begins to twist into something richer than clickbait. When people say Webb has looked back at Earth, what they really mean is that Webb has tested the methods we hope to use on worlds like ours. And the methods have delivered an uncomfortable lesson. A loud, swollen atmosphere is easier to detect than a thin, balanced, Earth-like one. In some cases, a dead world can be easier to read than a living, looking one. That feels backward. It feels like the universe has swapped the labels. You would think the richer, more interesting planet would announce itself more clearly. Instead, Webb's early rocky planet results suggested that the worlds most like Earth in the way we care about most may also be the worlds hardest to confirm with confidence. Home might hide better than ruin. The reason starts with the stars. The Planetary Society laid it out plainly. Many of the rocky planets Webb has studied closely orbit M dwarfs, the small, cool stars we thought would help us. But M dwarfs are often active. They flare. They throw out high-energy radiation. Over time, that can strip away the atmospheres of close-in worlds. So the very stars that make planets easier to spot can make those planets harder to keep alive in the way we imagine. Expected shortcut, actual trap. A convenient target turns into a rough neighborhood. It is like finding an apartment with cheap rent right beside a factory that never stops shaking the windows. There is another twist. According to Evgenia Shkolnik of Arizona State University, Webb is most sensitive to the kinds of big, puffy atmospheres that active M dwarfs are also most likely to erode. A thinner atmosphere more like Earth's could still exist on some of the planets Webb has studied. But if that atmosphere is faint enough, Webb may not be the instrument that can shout, "There it is!" with the certainty the public wants. That is the impossible feeling part. Webb can detect extraordinary detail in the right conditions. It can measure the thermal emission of a planet as small as Earth. Yet the kind of calm, modest atmosphere we associate with our own survival may remain subtle enough to dodge a clean detection. The telescope is not too weak for space. Our expectations were too simple for reality. Nicole Lewis warned about this kind of ambiguity before the results matured. Even if Webb sees gases out of balance, she said, scientists cannot instantly claim life. There may be non-biological causes. Surface processes can mimic living chemistry. Atmospheric reactions can play tricks. The universe has more than one way to make a strange signal. That warning becomes more important the longer you sit with Webb's rocky planets. Because what Webb has delivered is not a cartoon answer. It has delivered a filter. Some worlds fail the first test. Some worlds remain unclear. Some worlds may still hold thin atmospheres, but not the kind you can read in one triumphant headline. This is slower science, and better science. About 2/3 of the way through this story, honesty matters more than drama. Even the people doing this work do not fully agree on every interpretation, and they do not fully understand every atmosphere yet. That is not weakness. That is the sound of a field growing up in public. It is the difference between pretending to know and measuring carefully enough to notice how much is still uncertain. That uncertainty showed up even around TRAPPIST-1b. One set of observations pushed strongly toward bare rock. Later reporting from Max Planck researchers suggested the atmosphere question might be more complicated than the first simple reading. Not settled, not wrapped, not a neat ending. More like a door left open after everyone thought it had clicked shut. Still, the larger lesson has held. Webb's early rocky planet work has not handed us an easy Earth analog. It has shown that many of the first places we looked may be harsher than hoped, and that thin Earth-like atmospheres are difficult to confirm. Expected open book, actual faded pencil marks. You can still read them, maybe, but not by glancing once. This is where James Webb truly looked back at Earth. Not with a forbidden portrait of oceans and clouds, with a brutal calibration of our own ambition. If Earth were out there as only a small, rocky world with a modest atmosphere, around the wrong star or seen by the wrong method, even our finest machine could struggle to say what it was looking at. And once you realize that, another emotional shift happens. The silence is no longer disappointing. It is informative. A blank or nearly blank result is not empty. It tells us which kinds of worlds lose their air, which stars erase their planets, which methods hit the wall first, and how careful we must be before claiming we have found a second home. The comparison becomes almost domestic. Imagine trying to tell whether a house is lived in by standing half a mile away at dusk. A floodlit mansion gives itself away. A small home with one warm lamp behind a curtain does not. The missing signal does not mean the house is empty. It means your distance, your angle, and your tool all matter. That is why the phrase, "shouldn't be possible," lands in this story with a strange truth. It should not feel possible that a telescope this advanced could read giant alien atmospheres and still struggle with the thin kind of air we breathe. But that is exactly the lesson. Nature is not organized around our sense of fairness. It is organized around signal, noise, heat, chemistry, geometry, and time. And here is where this stops being about one telescope and begins being about us. If the reveal in this story is right, then the search for another Earth was never going to be a simple march from bigger mirrors to easy answers. It was always going to become a lesson in humility, patience, and better tools. Share this with the one friend who still thinks finding another Earth is just a camera problem. Passing it on this way turns a cool headline into a deeper conversation about how science actually moves. What Webb has done is not close the door. It has shown us which door was never as open as we thought. And now, the future shifts from find a louder signal to build a smarter way to hear a quieter world. That future is already being planned in two directions. One is on Earth, one is in space. Both exist because Webb has shown the field exactly where the hard part begins, not in fantasy, but in measurement. On the ground, the European Southern Observatory's Extremely Large Telescope, or ELT, is expected to become a major next step when it is completed in 2029. The plan is different from simply waiting for planets to transit. Scientists want to study worlds more directly and search for reflected light, which is starlight bouncing off a planet. That is closer to how Earth itself would first show up from far away. Jane Birkby of Oxford University and Ignaz Snellen of Leiden Observatory are among the researchers tied to that future. Snellen has said it will be possible, but very difficult. That sentence matters. Not impossible, not easy. Possible, but difficult, which may be the most honest slogan the search has ever had. The challenge is that even if the ELT reaches thinner atmospheres than Webb can cleanly detect, many of the same noisy stars still complicate the picture. M dwarfs flicker and flare. Their activity can imitate or drown out the planet's own signal. So the future is not just about a larger mirror. It is about smarter filtering, better modeling, and the patience to distrust the first exciting answer. In space, NASA's Habitable Worlds Observatory is being built in concept for an even more ambitious goal. The Planetary Society reports that it is under development for launch in the 2040s, or possibly earlier. Heidi Hammel, tied to both Aura and the Planetary Society, has been part of that conversation. Yevgenia Shkolnik has served as co-chair of a community science instrument team for the mission. That mission matters because it points away from the shortcut and toward the true challenge. Not just rocky worlds around small active stars, Earth-like planets around Sun-like stars. That is harder. The glare is worse, the geometry is meaner, but it is also where a real comparison to home begins to feel honest. You can feel the field changing its posture. The old dream was that Webb might simply reveal another Earth if we stared hard enough. The newer dream is tougher and more mature. Use Webb to map the limits. Use ground telescopes to reach into reflected light. Use future space observatories to hunt worlds that look less convenient and more meaningful. And meanwhile, Webb still matters every day. Its rocky planet results are not side notes on the way to the real discovery. They are the training data for the future. Every bare surface, every ruled-out thick atmosphere, every ambiguous signal tells engineers and astronomers what a successful next mission must be able to separate. There is also a domestic anchor here that is easy to miss. When you check the weather app before leaving the house, you trust thin layers of air to decide your whole day. Clouds, heat, moisture, pressure. A few invisible kilometers above your head shape your clothes, your drive, your mood, and your plans. That is how important an atmosphere is, even though you cannot hold it in your hand. Now stretch that thought outward. A planet's atmosphere is not decoration. It is the difference between a surface that keeps a memory of water and a surface that forgets it. It is the difference between heat being shared and heat being punished. It is the difference between a world that can stay chemically interesting and one that gets sandblasted into silence. As the calendar moves forward, the numbers get sharper. Webb sits roughly 1.5 million kilometers from Earth behind that sunshield. Its work on TRAPPIST-1b measured dayside brightness consistent with about 500 kelvins. Its work on TRAPPIST-1 sea-landed near 380 kelvins, with Nature reporting 380 plus or minus 31 kelvins. Those are not vague impressions, they are footholds. By 2029, if the ELT arrives on time, those footholds could become a new strategy. Not the same transit-first method, not the same dependence on swollen atmospheres, a push toward reflected light and higher precision from the ground, a chance to test whether some nearby rocky worlds hold the kind of thin air Webb could only hint at. Then comes the longer horizon. The 2040s sound far away until you remember how long hard telescopes take to become real. The Habitable Worlds Observatory is being shaped by the lesson Webb is teaching right now. The next machine must not only be powerful, it must be tuned for quiet worlds. It must be built for the faint kind of truth, and that changes what you, the viewer, might look for next. Be suspicious of headlines that skip from one strange gas to life found. Watch for the words atmosphere, thermal emission, reflected light, and uncertainty. Notice which star the planet orbits. Notice whether the world is giant or rocky. The future belongs to people who can tell the difference between a loud clue and a deep one. Because the search is not failing. It is narrowing. It is learning where not to overpromise. It is moving from wonder without brakes to wonder with instruments, dates, error bars, and sharper questions. That may feel slower, but slow is how a real map gets drawn. Tomorrow's picture of Earth from afar will not arrive all at once. It will arrive in pieces. A better spectrum here, a cleaner subtraction there, a direct light result on one carefully chosen world, a future mission designed because Webb taught us exactly which whisper we kept mistaking for a shout. Something new is going to happen in the years ahead. A larger telescope will separate a planet from its star a little more cleanly. A future observatory will read a thinner atmosphere more confidently. A world that now looks blank will begin to show structure. And when that day comes, it will feel less like magic than like a promise finally catching up with itself. The next horizon is not a postcard of Earth from Webb. It is stranger and better than that. It is the moment when our tools become sensitive enough to notice not just planets, but the kind of restraint that makes a planet habitable. Not a screaming atmosphere, a balanced one. Not a cosmic billboard, a quiet home. When that shift arrives, we may think back to these early Webb results with more gratitude than frustration. The bare rocks, the ruled-out thick carbon dioxide, the hard lesson from M dwarfs, the giant atmospheres that were easy to read. All of it was teaching us the same thing. You do not find a world like ours by wanting it harder. You find it by learning what makes it hard to see. So save this video and come back as the next round of measurements lands. That quiet bookmark will help you watch your own understanding sharpen with the science, instead of chasing every loud claim that flashes by. And when you do come back, carry one image with you. A gold telescope hanging in darkness, shield up, eyes outward, unable to stare at the Earth behind it. Not because it failed, because it was built to protect its cold vision from the heat of home. That design, which seems like a limit, is exactly what made the deeper lesson possible. James Webb did not give us the forbidden portrait people imagined. It gave us something more useful. It showed that Earth, as a scientific target, is not just precious, it is subtle. And subtle things demand better questions. Somewhere ahead, maybe in 2029, maybe later, maybe with a mission born in the 2040s, another instrument will catch what Webb only taught us to seek: a thin atmosphere, a careful imbalance, a reflected glint that survives every attempt to explain it away. And when that happens, the future will not feel distant at all. It will feel like the moment we finally learned how to recognize home.